Thanks for the introduction. Appreciate it. So I study ants, and studying social insects is one of those things where many times we're very captivated by really conspicuous and fascinating adaptations. We might be interested in the repeated evolution of winglessness in queens. We might be interested in how colonies partition the thermal environment over the course of the day. And we might be interested in various kinds of, or we might be looking at various kinds of symbioses between ants and their microorganisms or animals or plants that they engage in symbiotic interactions with. A lot of these sort of very charismatic sorts of adaptations, none of which I'm going to talk about today. Sort of none of that is really what the subject of this talk is about. One of the things we have trouble with when we're thinking about that sort of exploration of adaptation in social insects, let's say ants specifically, is the idea of, well, if you know that something is 25% more efficient, in doing something, what does that mean for the ants in nature? If it's twice as efficient at collecting food, that sounds good, but whether it's good or not really has a lot to do with this sort of balance between how much variability there is in terms of the fitness of particular ants that are in nature, and population sizes and effective population sizes, heritabilities, and so on of these traits. So my goal here is really something a little more, basic or sort of, I don't want to say fundamental, but it's just kind of basic. I mean, the question of to what extent do we see variation among colonies in fitness? And that's going to drive a lot of our notion of how much variation is out there in populations that would fuel natural selection, would result in potentially adaptation, and something that, to a very real extent, in social insects, and ants specifically, we don't have much information about. We don't really know much about how much differences there are among colonies in natural environments. Okay, and that's sort of the purpose of this. This project, I guess this is what I'm going to do. First of all, I'll give you kind of a general orientation to what this project is about. Then I'm going to talk about measuring fitness in populations of western harvester ant. Okay. Measuring survival, reproduction, and so on, which will be toward the purpose of asking how much variability is there in the fitness that we see out there. And it's going to turn out that there's a lot of variation. So the next question is, what's responsible for that? Okay, and the answer is going to be largely, it's due to differences in colony sizes, differences in colony growth rates. Okay, and then beyond that, I want to ask the question, why do they vary in size or growth rates? Okay, and two general categories of explanation might occur to you before you even heard of this topic, would be that there might be differences in environment, or there might be intrinsic differences among colonies. Okay, and that's going to turn out to be true. The overall message that I'm going to give you is something that probably you knew from the moment you entered an ecology or evolution program, which is that intrinsic differences among individuals are important, as is the environment. So that's not a terribly new message. What I'm trying to do, though, is kind of quantify the extent to which these differences in environment or intrinsic colony properties make a difference in terms of the survival and reproduction of this species. Okay. This is, I should say at the very outset, this is a study which is entirely in collaboration with Diane Mornis. Okay, and it's a joint project, and there's no part of it that's more hers or more mine or something like that. This is entirely joint work. Okay, it takes place in western Colorado, in Colorado Plateau. It is the sort of adobe badlands, if that means anything to people who have driven through that part of the world. Okay. We began this study in 1992, so we're now about 23 years into the study of this population. This is a map of the study site, which, this is in meters, and so it's about 800 by 800 meter area. It's a splotch here. The colonies are given, as these dots here. So there's a lot of colonies. Okay. At any one time, there are something on the order of 1,200 to 1,000 to 1,500 colonies. About 1,200 colonies alive at any one time. Through last summer, we had information on something like 5,500 colonies. Okay, so that means that something like 4,000 colonies have died, and 4,000 colonies have been added to the population. So it maintains a kind of overall, very overall standing crop of colonies in this population. So that's our data. That's what our data set is made up of. This is also to remind me to say that it's not a flat, featureless habitat. The colors are indicating the sort of topography, so from high to low areas. Okay. So there's hills and washes and so on. This is without those hills and washes. I'm just trying to give you a sense of the kinds of information that we are able to collect. Okay, so in a given year, we have the study site blocked off into these 50 meter by 50 meter quarter hectare plots, which we have maps of, and we carefully go over every square foot, really, of the study site, finding colonies that have survived, okay, those that have died, and sketching in the locations of those that are new colonies to the site. So, we record survival, and here's a colony that has survived, and there's its tag. Everything's tagged. Here's a record death. This unfortunate colony is dead. And map everybody who's new. Okay. Additionally, we measure the size of everybody every year. So the size is, ideally we would like to know what's the population of workers in the colony, but that's, in practical terms, not possible. What is possible is to measure estimate the size, the number of workers in the colony. We do that by measuring the size of this external nest cone. It's just length times width times height. Take the log of that. And it gives you a measure of colony size. It correlates very well with the number of foragers in a colony, so that's nice. Okay. Now colonies go from little tiny colonies that we see in their first year. Here's a penny, little colony, to big mature colonies. Okay, and its tag. So we also, from those size data, get information on colony growth. Okay, and this is just growth in one time interval, because every time interval looks pretty much the same. This is growth from 2006 to 2007. It's the size difference between those 2 years, okay? Plotted against the size, the original size, okay? First is that there's a big mush. It's a lot of variability here, okay? There always is. And the second is that there's always a negative correlation, or negative regression here of this absolute size difference on the initial size, okay? Big colonies don't grow as much as little colonies, okay? That's not a really very fundamental revelation here. But we use as our measure of actual growth here the residuals of these points from the regression of size change on initial size. Okay, so you can have, these have positive growth, absolute growth, but negative residuals. So they're not growing as much as they should. Okay. The important thing about that is that we can get this for every pair of years, and our measure of growth is independent of size. Okay, so that's something critical. Okay, reproduction. We actually have measured reproductive output in a detailed way for a subset of colonies. Here's our main study site, main study population, and we selected in 1993 a group of about 200 colonies, okay, that we're going to look in detail at their reproductive output. Some of those colonies are within the study site, some are just on the edge, others are isolated a bit, so we have them in different sort of geographical blocks. And over sort of this time interval, about 15 years, we looked at in detail at the reproduction over about 10 of those years. The way we do that is by taking advantage of the fact that reproduction in this harvester ant is cued by summer monsoonal rains. Okay, so rain comes and then the next day the reproductives fly. So what we do is we go out to colonies, a backpack sprayer full of water, and water it. Okay, it works. The next day, they send out the reproductives. We catch them in a reproductive trap. It's basically a fish trap. If you're that sort of that sorts of arrangements here. Okay. So here's a lot of reproductives up in this top of this cone. We can take a cone off and count all of the reproduction, get the number, find out whether they're making males or females. We put everybody into these 96-well microtiter plates, hundreds of them, and dry the reproductives and weigh everybody, so we have some sense of their size as well. Okay. So that's a lot of effort to get information about the reproduction of those 200 colonies. Now, those 200 colonies are things that we started with in 1993. They're not, in any sense, a random sample or representative, maybe, sample of everybody in the population in terms of their sizes. They're bigger colonies to begin with, because there were colonies that we wanted to actually have to be big enough that we would get reproduction to start with. Okay. We have another set of reproductive data, which is based on scan samples. During the real mating flight, the queens and males come out of the nest at about 3 o'clock in the afternoon, and they're there and detectable for about an hour. So we run around to as many colonies as we can and find out whether colonies either reproduced or didn't reproduce. So we have information on sort of a binary level about the amount, about whether or not they reproduced. Okay. So that kind of gives you the kind of information that we have available to us. Okay. Let's take a look at we start looking at how that survival and reproduction plays out, though. This is a survival curve for colonies, but really they're the survival curve of a queen, because there's a single queen in the colony and her life coincide basically with the life of the colony. Here she is excavating her nest on probably the day after the mating flight. Okay. There are maybe thousands of queens that you can find out on the desert floor who are starting their colonies. About 98 to 99% of them die in their first year, so before they produce a 1-year-old colony. And then, you have survival, overall cohort survival declines as well as you get out to greater ages. As far as we can tell, they live to be about 40 years old, maximum. Okay. And you can see that one of the things that's happening is that, there's very little survival to start with. Survival goes up. They get a greater and greater chance of survival. We'll see this in a little clearer way in just a bit. What about reproduction? Okay, and this is based from those scan samples. And the scan samples include colonies whose ages we know. Okay, so they're colonies who we've studied long enough that we can know what age they are. Okay, so we can look at the probability that they're going to be produced. Not, again, can't measure the amount that they reproduce, but the probability that they reproduce as a function of age. And it basically is drifting upwards. Okay. So we have a first shot here at looking at something like fitness components. We have survival, probabilities, and probability of reproduction as a function of age. Okay. And it doesn't say a tremendous amount, but it does allow you to say a couple of things that might be of some interest here. First of all is that if you look at colonies that are more than 5 years old, they have a very good chance of surviving. Very high survival from year to year, 90% or more. Okay. That means that in all likelihood, there's not a lot that's going to influence the fitness of colonies out here, because pretty much everybody's going to survive. There's not going to be a lot of differences here, especially if compared to the differences, the effect that you might see here when they're 0 to 1 year of age. Okay. Differences, that's different from the way it is with reproduction. So probability of reproduction never rises above 50%, really. And so there's a lot of opportunity for there to be differences in fitness here according to reproduction. Okay, let's take a little closer look at their reproductive output. Now these are from colonies that are, I'm sorry, I'm supposed to stay within sight of the camera. It's hard for me to do because I'll do this. These are the colonies that are that we were looking in detail at their reproductive output. Okay, this is a Lorenz plot. You've probably seen this. Basically, we're looking at colonies ranked by their amount of reproduction that they have, and this is the cumulative fraction of colonies. And this is the cumulative fraction of reproduction that those colonies are responsible for. So that if everybody's dividing reproduction equally, 50% of the colonies will make 50% of the reproduction. For the harvester ants, the reproduction through male and female function is substantially different from equal. Okay, there's a lot of variability among colonies in how much they reproduce. A lot of colonies, 45% of the colonies don't reproduce. And importantly, half of the reproduction, of colonies of the population is due to something like 10% of the total colonies. Okay. Now, that suggests that there's tremendous differences in fitness among colonies. Some colonies are really important to the sort of overall reproductive output of that population. Other colonies just aren't really terribly relevant. Okay. Males are a little bit there's a little bit of a difference between males and females, but really what the point you should see here is that there's real big differences among colonies. Okay. Looking at this a little bit more, I don't know, traditionally, perhaps, we look at the sort of output of reproduction through females for a colony compared to output through males for that same colony. So each point represents a colony. Each point represents all of the data across those about 10 years of detailed reproductive assays. And it's a log scale. There's obviously a very high correlation between male and female reproductive output. So, there are colonies that have high reproduction, and that reproduction is both through male and through females. And there's some that have very low production both through males and females. You don't have anything like colonies that make all females and no males, or all males and no females. You don't have that sort of split sex ratios in this species. Okay. There's a lot of variability here, okay, among colonies. Okay, we actually have the opportunity to ask what is responsible for that variation in reproductive output. Okay, we can ask the question, is it due to the fact that some colonies just survive longer than others? Is it due to the fact that, and therefore they have more opportunities for reproducing? Okay? Or is it due to greater reproductive output per reproductive opportunity? And the answer to both of those is yes. I mean, if you look at these, are standardized partial regressions. So longer survival matters for both male output and for female output. By chance, they end up being the same coefficient. It's higher in terms of what's responsible for their total fitness in terms of the greater reproductive output per year. But both of them are actually pretty important. Males are a little, their fitness through male function is a little bit more due to greater output per year than it is for females. Okay. So survival rates vary and reproductive rates vary. Why is that? First of all, I have to make sure to tell you that this represents a size-based demography. Okay. I was plotting a lot of things as a function of age, but that's really not very informative in many cases. The thing that really matters to the reproduction of harvester ants is really the size of the colony. Okay. If you look at colonies of different size with the same age, the one that's bigger is going to reproduce more. If you look at colonies of different ages but the same size, they tend to reproduce the same amount. So really age doesn't matter, it's size that matters. So why are there differences in size? Okay. Okay, so size matters to both survival and reproductive output of the colonies. Okay. These are regressions of fitness, survival, or reproductive output on phenotype. Okay. So these are selection coefficients. Okay. It turns out that colony size, again, by chance, turns out to have the same coefficient, selection coefficient on survival as it does on reproduction. Okay. Not surprising. Now, why do colonies differ in size? Well, one of the obvious reasons that they differ in size is because some colonies grow faster, and those colonies that grow faster get to be bigger sizes. Okay. Now, this takes us back to our measures of colony growth. Okay, so how do you read this? this says 2010. So this means that we can measure growth from 2010 to 2011. Okay, and they'll vary in that measure of growth. Okay, and we ask whether or not that measure influences whether they then survive to 2012. Okay, so you need 3 years of data here. 2010 to 2011, does that mean that they're going to survive to 2012? Okay. Again, this is, when we do it in the proper units, it ends up with a selection coefficient because it's a regression of fitness on phenotype. And so we end up with these as selection coefficients with their 95% confidence limits. Okay. Keeping in mind that these measures of growth are independent of size. Yeah. And you can see the conclusion. In most years, the colonies that grow faster also are those that are going to survive better, okay, independent of size. Not always, which is actually sort of reassuring in some ways. That means that colony growth has an effect on survival that's independent of colony size. Now, of course, colony growth influences colony size. I mean, this is not really fitness, so it's just a regression here. Okay, colony growth does influence colony size. And reproduction then is influenced by colony size and indirectly by colony growth, but there's no direct component as opposed to in survival, there is that direct effect of colony growth on survival. Okay. So colony growth and colony size vary a lot. Why do locations differ in those traits? Why do colonies differ in those traits? It may be that there are locations that are better or worse for ants. And that seems entirely reasonable. If you take ants and put them in certain locations, you're going to have higher reproductive output or greater survival. Others are going to be bad for ants, and they're going to have low reproduction, low survival rates. On the other hand, there might be intrinsic differences. This is a good colony, and no matter where it ended up, it was just going to have a high reproductive rate. These are harvester ants. They eat seeds. And so there's a reasonable expectation that vegetation might matter to colonies. Those colonies that have particular kind of vegetation might actually be in a favorable situation for survival or growth. Okay. There could be other things that are happening. There are other differences among locations that are not just due to vegetation. Depth of soil, concentration at our site, the concentration of selenium in the soil matters. The aspect of a slope or something like that, that might matter. In fact, we don't measure these sorts of things, but in truth, we will look at vegetation, and vegetation does pay attention to soil depth and nutrient properties of soils and so on. So when we talk about locations, much of the time we'll be looking at the relation to vegetation, but in truth, we don't know that it's vegetation per se. It could be something that's co-varying tightly with vegetation. Okay. Another trait that might vary among locations is density of conspecifics. This is a trait which is, the colony that you're interested in doesn't have any control over, and so it may influence the quality of that location. There might be intrinsic colony differences. One of the leading possibilities for intrinsic differences among colonies is mating frequency. But remember that while this is an intrinsic difference in the colony that the colony can't change, okay, it's not something that necessarily will be absolutely stable from one generation to the next either, because it's mating frequency. Okay. And then the possibility that there are just qualitative differences in the queens that found the nests. Okay. We'll kind of go through these quickly. Okay. Now, idea here that there might be differences in the performance of colonies, as a consequence of the fact that they may have different amounts of food because of vegetation. And actually, food is a reasonable idea here. This is a kind of complicated figure that summarizes a food supplement experiment where it shows basically that food matters to reproduction. We supplemented with, so it's looking at male reproductive output or female reproductive output, two kinds of food supplements, wheat supplements or mealworms. We looked at colonies for 2 years prior to the food supplement, okay? And what we're measuring here is the difference among the food supplement versus the control colonies. So before we added food, there was no difference between colonies in terms of what they were going to, in terms of their reproduction on the basis of what experimental group they were going to be in the future. That's good. We added food for 3 years, and it changed reproductive output substantially, wheat at least. Then we stopped supplementing food, and we looked at their reproductive output for another 5 years. And surprisingly to us, it didn't go all the way back down to zero. It looked like there was an effect of the food availability on colonies' reproductive output, but in addition, there's apparently some sort of a developmental switch in colonies that made some colonies change over to be more likely to reproduce even given their size after they've had an abundance of food at one time during their lifetime. So food should matter. Okay. This is the same geographical site, but now we're looking at vegetation map, about 15,000 vegetation quadrats, and what we're just looking at here is just a map of PC1. Okay. The hotter colors are high loadings, bromus and sarcobatus, greasewood. Okay. Cooler colors, Atriplex, Rhiza, Hilaria. These are kind of common native vegetation that's even a little bit more uplands. And you can see that there's definitely differences in the geographical differences in vegetation, and it parallels to topographic differences. This outline of a wash, and there's hills between, or washes are between hills, and so there's more than just vegetation information contained within PC1. Okay. So we take that information about vegetation and try to see if we find any information about the relationship between vegetation and these fitness traits. And what seems to matter is that reproductive output is influenced by vegetation, or it's influenced by those other environmental traits that co-vary with vegetation. Hotter scores have higher reproduction, and these are for the last 2 years. 2014 was more reproduction than 2013, but it shows the same sort of pattern. Cooler scores have lower reproduction. Nothing else seems to matter, though. If you look at survival, there's no real pattern with vegetation. If you look at growth, nothing that stands out, nothing that's very consistent. So one fitness component seems to matter, reproduction, but survival and this sort of indirect measure, growth, doesn't seem to be influenced by the properties of the location. And incidentally, conspecific density in the location of a nest also doesn't seem to matter. And this actually surprised me quite a bit, that I would have thought that high density areas would have lower survival or reproduction. It just seems not to be the case. Okay. What about intrinsic colony differences here? So there's some differences here. What about intrinsic colony differences? Okay. Mating frequency has often been sort of implicated in the increased colony efficiency for a variety of organisms, including harvester ants. And we suspected that it might be as well. So here we are looking at either fitness measures or fitness correlates, okay, in terms of the number of patrolines there are in a colony. So for those 200 colonies for which we have detailed reproductive measures, we also have genotyped all of those colonies, okay? We know how many times the queen mated, okay? So in those colonies, what we can do is we can take a look at those male and female production measures that we saw earlier, okay, and regress them on the phenotype, the number of patrolines in the colony, okay, the number of times that the queen mated, okay, and those give us selection coefficients. For male and female production, those are significant effects. For survival, it's not so significant. I just point out here that all the reproduction is happening among those colonies whose sizes we chose to study with our reproductive data set. Much of the survival differences are happening far earlier than those colonies that we selected for the reproductive data set. So maybe that's something that's going on here. We don't really know. Also, for those colonies that we investigate their reproduction in detail, we know their colony growth rates and colony sizes, and those also have significant regression with on number of patrolines. This isn't really a selection coefficient, but it's certainly related to there's a relation to a fitness correlate here. This last sort of grayed out one has to do with allozymes. Originally, when we first started looking at this system, we didn't have microsatellites. We couldn't measure the number of patrolines in the colony. We had allozymes. You remember allozymes? A few of us gray-haired people remember allozymes. We could use those to measure relatedness. We found out that colonies with high degree of relatedness had low growth rates. High degree of relatedness means that the queen didn't mate as often. Low degree of relatedness meant that they were queen mated more frequently and they had higher growth rates. Okay. We looked at about 1,500 colonies, however, with allozymes. And those colonies are still there, surviving and growing and reproducing. So we took a look at, we actually can measure growth in each of 20 years subsequent to our original study on this. Okay. Some years we get a negative relationship, significant. Other years it's not so significant. But overall, it's a highly significant relationship between relatedness in a colony and colony growth. Negative relationship. Okay, when you combine probabilities across all of the years. Okay, it's really a robust relationship between colony growth and colony relatedness. You can't talk about it as a selection coefficient here because there's no kind of linear relationship between relatedness and patrolline number. So it's a little harder to interpret. Okay. So there are intrinsic differences among colonies. There are these mating frequency differences that cause differences in fitness. Possibly, go back to by modulating patterns of colony growth, resulting in increased colony size, which then cascades into increased reproductive output. Okay, what about queen quality? The notion that there might be just goodies out there. There might be good queens and bad queens. How do you approach that sort of thing? Here we really need to have some sort of a experimental, manipulative approach to things. And this is something that Diane Warnes has really worked out here. We use directed matings. Okay, we water colonies. The queens come out first, so you can collect queens from a known colony now. Okay, And once you've got enough queens, you put the cone on, you get males. Okay? Then in our mobile laboratory, we successively put queens from a particular source colony, which are matrilides, okay, successively exposed to males from different colonies. Okay? So here they are. So there's some queens in here, and they're being crossed with males from another colony. And they'd be kind of like hopscotch around. Okay. Fly them back to the Houston, the queens, that is, and use them to start colonies. Actually, here's the queen. And she's been reasonably successful. And then when they get to be this size, then we can do things to them. Okay? You can do things to them. You can, for one thing, just measure the size of the colony. Okay? They all started at the same time, so if they have different sizes, that means they have different growth rates. Okay? You can also do a bunch of behavioral assays. You can also collect workers from these colonies and genotype them, find out how many times this queen made it. Really important. So these are kind of the results for colony growth rates, basically. From 169 colonies in this data set, okay, 37 source colonies, so that's 37 different natural lineages. And that's what is summarized here, is the average colony size of the colonies that are headed by queens that came from a particular source. Okay? Measure colony size weekly, but here at 170 days. Okay. Some matrilines just don't do very well. You know, they have very small colony sizes. You know, this is not the colony size. This is the average colony size for however many colonies came from that source of queens. Others are doing really well. Okay. There's obviously a substantial difference among lineages here. Okay. A really whoppingly significant difference among lineages. You know, if you're looking at, this is in the lab. If you're looking at colonies in nature, you know, these colonies are not going to be little tiny colonies here at the end. They're going to be dead, basically. You know, this is a dead colony. Some of these actually were dead, or dead lineages. Some of these actually were dead lineages. The lineages that are going to actually disproportionately contribute to what? The next generation are a very small subset of the total in all likelihood. Okay. We have this till 1, right? Okay, so let's kind of finish up here. So what do we know? Kind of the stuff we know more about it, but we don't in some ways know big categories more than we did when we started out. We know that colony fitness is highly inherent, is highly variable, and it's influenced by the environment and intrinsic properties of colonies and queens and so on. So it's not a surprise, but it's kind of nice to know a little bit of detailed information on how that works. What do we don't know? What we don't know? We don't know which of these is really so much important here. We don't know about interactions necessarily between some of these traits. We'd like to know that. We'd like to be able to get some sort of experimental verification of some of these, what are largely correlative data. Okay. So that's actually leading us to the future, which is what we're going to make use of those, the ability to form colonies with directed matings. We're going to construct these colonies, okay, and then experimentally, as we construct the colonies, we can manipulate genetic diversity and queen quality, okay? And then we grow them in the lab until they get to a point where we can feel good about transplanting them back out into nature. Okay, and then we're going to measure them for whatever years. Okay, so we grow them as you saw before, and then we put them into cardboard containers with dirt in it. We put the ants in the dirt, and they dig a nest, a starter nest. You do a bunch of those, take them out to the field, and you cut a hole in them, or cut the bottom of that container off, dig a hole, and you plant them in the ground, and you've got a transplanted colony. That we can give food to or not, manipulate environmental qualities. We have manipulated the mating frequency. We can determine exactly where this colony is placed. We can experimentally manipulate the identity of the source colonies. Okay. So we expect to be able to do these sorts of things. We might look at, food addition or not, source lineages, the source colonies that are high quality or low quality, and we can vary experimentally the mating frequencies. Okay. We might find, I don't know what this is, food addition effect, or mating frequency effect, or a queen quality effect, or what is this? This is like a food addition effect, queen quality. No, we have a mating frequency effect, and we have like a quality by mating frequency by food addition effect, or something weird. Okay. This is an experiment that takes a long time to undertake. So we began this first round of them in 2013, where we collected the queens, made the crosses, grew them for a year, transplanted them in this last summer. Here's our first group of transplants. And we're going to do another round of them from colonies that we constructed this summer, and hopefully we'll have about 200 to 300, I will hope, that we can transplant next summer. Okay? And then we're going to follow them for the next X years, 10 years, I said, and measure a variety of things: survival, growth, reproduction, and so on. Okay? And maybe whatever else we can think of. Okay? To see if we can now experimentally pull apart the independent effects of mating frequency or food addition or environmental quality or queen quality and so on. Okay? So I want to thank particularly Diane Mortis, who's a complete collaborator in all of this work. A variety of people who have taken data through the years. The Bureau of Land Management has let us work on BLM land for 20-some years now, and we're part of their management plan, which is good. NSF has given us an LTREB that lets us think 10 years into the future. And the state of Texas has given Diana money a couple of times, which has really been very useful. So that's all I want to say. Thank you. I don't know how much time we have, but
I think we can just take one question. I know we have a class coming in after.
So it's fantastic set of data that you have. Did you determine what average colony size was? Do you know on average what the colony of harvester ants in this location is?
Yes. An average, so they start out at 0 workers, and they get up to a maximum 20, 30,000 workers. Okay. The average is what over the?
Or is it over lifespan?
Over the lifespan, it changes. It gets very large, and then eventually at the end it gets smaller again. Okay. I don't know if that's a meaningful place to put an average. But if somebody put a gun to my head and say you have to give me an average, it would probably be about 10,000.
Great. Let's thank Dr. Collian for his seminar.
I'm sorry there was no more time for questions, but
Pizza lunch upstairs.
Thanks for the introduction.
Yeah.
Appreciate it. So I study ants, and studying social insects is one of those things where many times we're very captivated by really conspicuous and fascinating adaptations. We might be interested in the repeated evolution of winglessness in queens. We might be interested in how colonies partition the thermal environment over the course of the day. And we might be interested in various kinds of, or we might be looking at various kinds of symbioses between ants and their microorganisms or animals or plants that they engage in symbiotic interactions with. A lot of these sort of very charismatic sorts of adaptations, none of which I'm going to talk about today. Sort of none of that is really what the subject of this talk is about. One of the things we have trouble with when we're thinking about that sort of Colorado Plateau, it is the sort of adobe badlands, if that means anything to people who have driven through that part of the world. Okay. We began this study in 1992, so we're now about 23 years into the study of this population. This is a map of the study site, which, this is in meters, and so it's about 800 by 800 meter area. It's a splotch here. The colonies are given, as these dots here. So there's a lot of colonies. Okay. At any one time, there are something on the order of 1,200 to 1,000 to 1,500 colonies. About 1,200 colonies alive at any one time. Through last summer, we had information on something like 5,500 colonies. Okay, so that means that something like 4,000 colonies have died, and 4,000 colonies have been added to the population. So it maintains a kind of overall, very overall standing crop of colonies in this population. So that's our data. That's what our data set is made up of. Vary in size or growth rates. Okay, and two general categories of explanation might occur to you before you even heard of this topic. Would be that there might be differences in environment, or there might be intrinsic differences among colonies. Okay, and that's going to turn out to be true. The overall message that I'm going to give you is something that probably you knew from the moment you entered an ecology or evolution program, which is that intrinsic differences among individuals are important, as is the environment. So that's not a terribly new message. What I'm trying to do, though, is kind of quantify the extent to which these differences in environment or intrinsic colony properties make a difference in terms of the survival and reproduction of this species. Okay. This is, I should say at the very outset, this is a study which is entirely in collaboration with Diane Morness. Okay, and it's a joint project, and there's no part of it that's more hers or more mine or something like that. This is entirely joint work. Okay, it takes place in western Colorado, in potentially adaptation, and something that, to a very real extent, in social insects, and ants specifically, we don't have much information about. We don't really know much about how much differences there are among colonies in natural environments. Okay, and that's sort of the purpose of this. This project, I guess this is what I'm going to do. First of all, I'll give you kind of a general orientation to what this project is about. Then I'm going to talk about measuring fitness in populations of western harvester ant. Okay. Measuring survival, reproduction, and so on, which will be toward the purpose of asking how much variability is there in the fitness that we see out there. And it's going to turn out that there's a lot of variation. So the next question is, what's responsible for that? Okay, and the answer is going to be largely, it's due to differences in colony sizes, differences in colony growth rates. Okay, and then beyond that, I want to ask the question, why did the exploration of adaptation in social insects, let's say ants specifically, is the idea of, well, if you know that something is 25% more efficient, in doing something, what does that mean for the ants in nature? If it's twice as efficient at collecting food, that sounds good, but whether it's good or not really has a lot to do with the sort of balance between how much variability there is in terms of the fitness of particular ants that are in nature, and population sizes and effective population sizes, heritabilities, and so on of these traits. So my goal here is really something a little more, basic or sort of, I don't want to say fundamental, but it's just kind of basic. I mean, the question of, to what extent do we see variation among colonies in fitness? And that's going to drive a lot of our notion of how much variation is out there in populations that would fuel natural selection, would result in